Hey, my friend, forget your stress, get comfortable, and let your eyes get heavy. Tonight, we're drifting through Marie Curie's discovery of radioactivity, how atoms quietly change themselves, and what that means for our world. You don't need to stay awake, just listen, and let the science carry you to sleep. Chapter 1. Marie Curie and the Hidden Phenomenon. At the end of the 19th century, Europe was full of confident explanations. Physics had mapped the motion of planets and the swing of pendulums with a precision that felt almost complete. Chemistry could name elements, weigh them, and predict how they would combine. In laboratories across Paris, Berlin, London, and Vienna, the world seemed increasingly legible, as if nature were a book whose last pages were already within reach. And then the book began to change its language. Scientists were learning how to make the invisible show itself. Glass tubes pumped thin of air could glow under high voltage, producing unfamiliar effects. The newly discovered X-rays revealed bones through flesh and turned bodies into shadows on photographic plates. It suggested that reality had layers that human senses could never directly touch. Yet instruments could translate into evidence. The universe, quietly, was admitting it had hidden rooms. Into that atmosphere stepped Marie Skłodowska, later known as Marie Curie. She was born in Warsaw, in a Poland that existed culturally and historically, but not as an independent state on the political map of Europe. Her education was shaped by both ambition and restriction, and she trained wherever knowledge could be found before traveling to Paris to study physics and mathematics at the Sorbonne. The story is often told as a simple climb of genius, but it was also endurance, learning to trust measurement over mood and persistence over spectacle. Marie's scientific temperament matched the moment. She had a rare ability to take a vague phenomenon and turn it into a stable question. She did not start by chasing mysteries in the abstract. She started by choosing something that could be measured, then insisting that measurement should be repeated, compared, and made reliable. That approach became essential when a new kind of phenomenon appeared that could not be seen, smelled, heard, or felt, and yet unmistakably acted on matter. The first clue came from uranium salts. Henri Becquerel had observed that compounds containing uranium could fog photographic plates, even when kept in darkness, and wrapped to block ordinary light. The effect looked like a spontaneous emission, as though the material were sending something out from itself, something able to pass through barriers and affect other substances. It was puzzling, but puzzles in science can remain curiosities unless someone decides they are the beginning of a new framework. Marie Curie decided that. She took the phenomenon and treated it not as a trick of uranium, but as an object of study. Her crucial choice was methodological. Instead of relying primarily on photographic plates, which offered dramatic results but limited precision, she used a strategy based on how the emission made air conductive. When certain rays pass through air, they can knock electrons free from atoms and molecules, creating ions. That process allows a faint electric current to flow. If you can measure that current, you can quantify the strength of the emission without needing your eyes at all. Astonishment becomes data. This is where the Curie laboratory becomes a turning point in modern science, a place where invisible processes were given a language of instruments. Marie's work was aided by tools associated with Pierre Curie, the physicist she married in Paris. Pierre and his brother had developed sensitive devices for measuring tiny electrical effects, including a quartz electrometer that could detect extremely faint currents. With such an instrument, Marie could compare samples systematically. She could ask not only whether a substance produced an effect, but how much effect it produced, and whether that effect changed with chemical form or processing. The results were immediate and unsettling. Uranium compounds behaved as if the emission did not depend strongly on the way the atoms were arranged in a crystal or bound in a molecule. The strength of the emission seemed tied to the element itself, not to chemistry. That was a profound clue. Chemistry is the study of how atoms combine, yet here was an effect that appeared to come from deeper within the atom, from something more fundamental than bonding or structure. In that era, atoms were still often imagined as stable, smallest units of matter, but Marie's measurements suggested that some atoms were active sources of penetrating energy. To describe this new category of behavior, Marie coined a word: radioactivity. The word did not solve the mystery, but it framed it. It told the scientific community that this was not an odd chemical reaction or trapped light in a crystal. It was an intrinsic property of certain atoms, involving spontaneous emission of ionizing, penetrating radiation from certain kinds of matter. Matter could be unstable in a way that did not require heating, mixing, striking, or igniting. It could change quietly from within. When science meets a new phenomenon, the next question is whether it is rare or widespread. Marie pursued this with relentless calm. She tested not only uranium, but other minerals known to contain uranium, and she compared their activity. One mineral in particular, pitchblende, produced a much stronger effect than could be explained by its uranium content alone. This was the kind of discrepancy that can either be ignored as noise or treated as a message from nature. Marie treated it as a message. If pitchblende was more radioactive than uranium, then pitchblende must contain something else, something unknown and far more active. That conclusion did not come from speculation. It came from the logic of measurement. If the instrument is reliable and the comparisons are careful, then the mismatch is evidence. Here the narrative is sometimes romanticized. A couple in a drafty shed, stirring ore, chasing faint traces of new elements. The reality was physically demanding, but it was also chemically sophisticated. Separating new elements from a complex mineral requires repeated purification, precipitation, and crystallization, and the patience to track small signals through large masses of material. Marie and Pierre were not merely looking for a new substance. They were performing a long, disciplined search, guided by quantitative readings. Each chemical step was judged by whether the activity moved with a fraction or stayed behind. The radioactivity itself became a beacon that told them where the unknown element was hiding. The first success was polonium, named in honor of Marie's homeland, a scientific naming that carried both chemical meaning and political memory. The second was radium, named for its intense rays. These discoveries were not just additions to the periodic table. They were proof that radioactivity could reveal elements that ordinary chemistry might overlook because they exist in tiny quantities. The discoveries also demonstrated something deeper. The atom had internal processes. The rays were not a surface glow. They were signatures of transformations occurring at a level 19th century science had barely begun to imagine. As the field grew, other scientists began to classify the emissions and showed that radioactive substances could release different kinds of radiation with different penetrating power. That mattered because it confirmed that the hidden phenomenon was not a single simple effect. It was a new domain with structure, variety, and rules. Marie Curie's role in this early era was not only to discover elements, but to create a disciplined pathway from mystery to science. She brought radioactivity into the realm of standard measurement. She linked it to the identity of atoms rather than the arrangement of molecules. She insisted that an invisible process could still be studied with precision if one builds the right bridge between nature and instrument. Before radioactivity, energy release in matter was usually associated with chemistry, with burning, heat, and reaction. The atom, by contrast, was treated as stable. Marie Curie's work helped show that some atoms carry within them a kind of stored change, and that the release of that change can be spontaneous. Scientists would later build clearer models of atomic structure. But the first essential step was to accept the evidence. Matter itself could emit penetrating radiation without external prompting. The story also reveals something about how science advances. It is not only the grand idea that matters. It is the choice to measure, to compare, to repeat, and to trust what the measurements say, even when they contradict comfortable models. Marie Curie was exceptionally good at that. She was willing to treat a small, persistent anomaly as more important than a large, elegant assumption. Radioactivity, in this first chapter, is best understood as a doorway. Marie Curie did not yet have the full map of what lay behind it, but she opened it carefully, with instruments and logic rather than dramatics. She showed that the universe can reveal hidden behavior if you ask the right questions in the right way, and if you are patient enough to listen to answers that arrive as faint currents, subtle fogging, and small, undeniable differences. As you let these ideas settle, it can be strangely comforting to remember that nature does not rush. The deepest processes in matter unfold quietly, following their own rules, whether we notice them or not. You can let the day loosen its grip, knowing that the world is still there, steady beneath you, and that even its mysteries can be approached gently, one careful observation at a time. Chapter 2. What an atom really is. An atom is the smallest unit of a chemical element that still behaves like that element. If you take pure gold and keep dividing it, there is a point where what remains is no longer a smaller piece of gold in the everyday sense, but a single atom of gold. That atom still carries the identity of gold, not because it looks golden, but because it contains the specific internal structure that makes gold interact with other matter in a particular way. The modern idea of the atom is both simple and surprisingly deep. Simple because atoms are the building blocks of chemistry. Deep because the reason atoms behave as they do reaches into the most fundamental rules we have for matter. The story of atoms begins as a concept long before it became a measured object. For centuries, atoms were a philosophical answer to a practical question. If matter can be divided, does it ever stop being divisible? Chemistry in the modern sense eventually made the atom real by using it as an accounting system. When chemists learned that substances combine in consistent ratios by mass, and that these ratios repeat across experiments and locations, the simplest explanation was that matter comes in discrete units that combine in countable ways. The atom became a tool for making the world predictable. But the atom is not a tiny solid ball, and it is not a miniature solar system either, even though that image is sometimes used as a gentle stepping stone. An atom is mostly empty space in the sense that almost all of its mass is concentrated in a very small central region, while its electrons occupy a much larger region around it. Yet empty does not mean nothing. The space within an atom is filled with fields and quantum rules that shape where electrons can exist and how they can move. The atom is not a little object floating in a void. It is a structured pattern in the fabric of physical law. At the center of the atom is the nucleus. The nucleus is extremely small compared to the whole atom, but it contains nearly all of the atom's mass. The nucleus is made of protons and neutrons, which are collectively called nucleons. Protons carry a positive electric charge, and neutrons are electrically neutral. The number of protons in the nucleus defines the element. If the nucleus contains 1 proton, the atom is hydrogen. If it contains 6 protons, the atom is carbon. If it contains 79 protons, it is gold. This is the atom's identity tag, fixed not by chemistry or environment, but by the nucleus itself. The electrons are much lighter particles with a negative electric charge. They are not embedded inside the nucleus. They occupy the region around the nucleus, bound by the electromagnetic attraction between opposite charges. It is this electron region, not the nucleus, that directly governs most of chemistry. How atoms bond, how molecules form, why materials conduct electricity or resist it, why some substances are reactive and others are inert. The nucleus defines who the atom is. The electrons largely decide how that atom behaves in the chemical world. If this were all classical physics, the atom would be unstable. A negatively charged electron moving around a positively charged nucleus would be accelerating, and accelerating charges in classical electromagnetism radiate energy. If electrons behaved like tiny planets orbiting the sun, they would continuously lose energy and spiral into the nucleus. Atoms would collapse, and chemistry would not exist. The fact that atoms are stable is one of the quiet clues that the microscopic world follows different rules than intuition suggests. That difference is quantum mechanics. In quantum physics, electrons and atoms do not occupy well-defined paths like planets. Instead, they are described by quantum states that can be visualized as probability patterns. These patterns are sometimes called orbitals, but not because the electron is literally orbiting like a tiny moon. An orbital is better understood as a stable standing pattern that tells you where an electron is likely to be found if you measure its position. Between measurements, the electron is not a little bead tracing a curve. It is a quantum object whose behavior is governed by a wave-like mathematical description. Quantum states in atoms come with discrete energy levels. This is where the word quantized becomes meaningful in everyday terms. Electrons and atoms can only have certain allowed energies, not any energy at all. When an electron changes its state, it must move between these allowed energy levels. This is why atoms absorb and emit light in characteristic colors. Light can carry energy, and when an atom absorbs light, an electron may move to a higher energy state. When the electron returns to a lower energy state, the atom can emit light with a specific energy and therefore a specific wavelength and color. The atom becomes a natural barcode of itself, broadcasting its identity through the spectrum. The structure of allowed electron states also explains the architecture of the periodic table. Elements are arranged not only by the number of protons in the nucleus, but by recurring patterns in electron organization. When electron states in an outer region are filled in a certain way, the atom becomes chemically stable and less reactive. When the outer region has a vacancy or an extra electron it would rather give away, the atom becomes reactive, eager to bond. The periodic table is not just a catalog of substances, it is a map of how quantum rules shape matter into repeating behaviors. Now, the nucleus has its own story, and it is stranger in a different way. Protons are positively charged, so they repel each other through the electromagnetic force. If the nucleus contained only protons, it would fly apart. Neutrons help by adding an additional type of attraction at very short distances, connected to what is called the strong interaction. The strong interaction is immensely powerful at the scale of the nucleus, binding nucleons together so tightly that the nucleus can exist despite the electrical repulsion between protons. It is a force that dominates only within the tiny radius of the nucleus and becomes negligible at larger distances. This is why nuclei can be stable while atoms remain chemically active and spacious. Different forces govern different scales. The balance inside a nucleus is subtle. Too many protons without enough neutrons can lead to instability because repulsion grows. Too many neutrons can also cause instability because the nucleus can lower its energy by changing its composition. For many combinations of protons and neutrons, the nucleus is stable. For other combinations, it is unstable, and that instability is at the heart of radioactivity. To understand isotopes, imagine atoms of the same element that share the same number of protons, but have different numbers of neutrons. These variants are called isotopes. Carbon with one particular neutron count is stable and common. Carbon with a different neutron count is unstable and slowly transforms. Both are carbon because both have the same number of protons, but they differ in mass and in nuclear stability. Isotopes are not rare oddities. They are natural variations that exist in the environment, in the ground beneath you, in the air above you, and even inside living bodies. When a nucleus is unstable, it can transform into a different nucleus. This transformation is not driven by chemical conditions. You cannot make an unstable nucleus become stable by stirring, cooling, compressing, or mixing it in a beaker, at least not in ordinary chemical ways. Nuclear stability is governed by internal nuclear forces and quantum rules at the scale of nucleons. That is why nuclear phenomena feel so alien compared to chemistry. Chemistry rearranges electrons between atoms. Nuclear processes change the nucleus itself. Radioactive decay comes in different forms, but at its core it is a nucleus changing into a configuration with lower energy or greater stability. Sometimes a nucleus emits a tightly bound cluster of nucleons, which reduces its size. Sometimes a neutron changes into a proton, or a proton changes into a neutron, adjusting the balance between them. Sometimes the nucleus emits energy as a high-energy photon after rearranging internally. In each case, the atom's identity can change because the number of protons can change. An element can transform into another element, not as an alchemical dream, but as a physical process governed by the laws of nature. One of the most calming ideas in this subject is also one of the strangest. Decay is random at the level of a single nucleus, yet predictable in large collections. You cannot point at one unstable atom and know when it will transform. But if you have a very large number of identical unstable atoms, the fraction that transform over a given span of time follows a reliable statistical pattern. This is why radioactive materials can function as clocks, and why scientists can use decay to date rocks, artifacts, and even processes in the history of the planet. The randomness of single events becomes the reliability of large numbers, like raindrops unpredictable one by one but steady as a storm. It is important, too, to notice what atoms are not. They are not purely mechanical objects with hidden gears. They are not tiny hard marbles. They are quantum systems shaped by fields, forces, and probabilities that only become definite in measurement. Yet they are not vague or imaginary. The predictive success of atomic theory is overwhelming. From the spectra of stars to the workings of electronics, from chemical reactions in your cells to the materials in your phone, the atom is one of the best tested concepts in science. In a quiet way, atoms also redefine what solid means. The feeling of solidity in everyday life comes primarily from electromagnetic interactions between the electron clouds of atoms. When you press your hand against a table, your atoms do not interlock like bricks. They resist because electron states in matter obey quantum rules that prevent them from being forced into the same states. The table pushes back not because matter is packed like stone at the deepest level, but because the laws that govern electrons create stability and resistance. The ordinary world is held up by invisible structure, and within that ordinary stability, there is the nucleus, compact, energetic, and in some cases, slowly changing. That is the doorway into radioactivity, but even before we step through it, we can appreciate the atom as a kind of compromise the universe has found. It concentrates mass in a nucleus, spreads influence through electrons, and lets matter assemble into everything from rocks to living tissue. It is a minimal unit that still carries a full identity, and yet it is also a small universe of interactions inside. If you let your mind rest on this for a moment, there is something quietly existential about it. You are built from atoms that feel solid only because of rules you never have to think about, and stable only because forces you cannot see hold them together. The day's worries are loud, but they sit on top of a deeper calm. The fact that reality has structure, and that structure keeps you here, held gently in place by the same physical laws that shape stars, stones, and the air moving through your lungs. Chapter 3. The Discovery of Radioactivity. The discovery of radioactivity did not arrive as a single dramatic moment with a clear explanation attached. It arrived the way many foundational scientific ideas arrive, as an observation that did not fit the categories people already had, followed by a patient struggle to understand what exactly was being observed. In the late 19th century, physics and chemistry had become highly confident disciplines, but that confidence was built on a world that behaved predictably at human scale. When instruments began revealing phenomena that did not depend on heat, light, friction, or familiar chemical change, scientists encountered something both exciting and unsettling. Matter could do things silently, from within, without any obvious cause. This period was already rich with surprises. Electrical research had produced strange glowing tubes and unexpected effects. The discovery of X-rays showed that invisible radiation could pass through flesh and leave an imprint on photographic plates. These new rays were not light in the ordinary sense, and yet they behaved like something that traveled through space and interacted with matter. The world was suddenly full of invisible messengers. In that atmosphere, the discovery of radioactivity was not a random accident so much as an outcome waiting to happen, because the tools and questions were finally aligned to notice it. The first clear step is associated with Henri Becquerel. He was interested in a phenomenon known as phosphorescence, in which certain materials absorb energy and then re-emit it slowly as visible light. The idea that absorbed sunlight might lead to a secondary emission seemed plausible, and in the wake of X-rays, there was curiosity about whether phosphorescent materials might also emit penetrating rays capable of affecting photographic plates. Becquerel chose uranium salts as a candidate, partly because some uranium compounds show phosphorescence. His experimental approach relied on a simple, elegant idea. If uranium salts produce some kind of invisible radiation, then photographic plates should record it even without visible light. He placed uranium salts on photographic plates that were carefully wrapped to block ordinary light. When the plates were developed, images appeared. At first glance, it seemed consistent with the idea that sunlight had energized the salts, and that the salts then emitted some form of penetrating radiation. But the crucial turn in the story came when conditions changed. Weather interfered with the expected exposure to sunlight. Becquerel stored prepared samples away, waiting for the sun to return. Later, when he developed the plates that had been kept in darkness, the images were still present, and in some cases strongly so. The emission did not require prior exposure to sunlight. It was not a delayed glow. It was spontaneous. That shift mattered. A phenomenon tied to sunlight could be filed under luminescence or photochemistry. A phenomenon occurring in darkness without triggering energy suggested something intrinsic to the material itself. Uranium, it seemed, was emitting an invisible radiation continuously. The effect was not a trick of storage or the result of an ordinary chemical reaction. It appeared to be a persistent property of the element. It is tempting to imagine Becquerel immediately grasping the full meaning of this. In reality, early discoveries often carry uncertain interpretation. At the time, even the concept of radiation was expanding and unsettled. There were debates about whether these effects were waves, particles, or something else entirely. Photographic plates could show that something was happening, but they did not easily reveal the nature of what was happening. What made the discovery scientific rather than merely curious was that other researchers could reproduce it, vary conditions, test alternatives, and slowly isolate the essential features. One of the most important features was that the emission could ionize air. Ionization means that neutral atoms or molecules in air are converted into charged particles, which allows air to conduct electricity slightly. This property was crucial because it gave scientists a new way to detect the phenomenon quantitatively. Photographic plates are excellent for producing a visible record, but they can be affected by many factors and are not naturally numerical. Ionization, by contrast, can be measured as an electrical effect. The discovery of radioactivity, therefore, belongs not only to a moment of noticing, but also to a shift in methods, from seeing a fogged plate to measuring an invisible current. Marie Curie entered at this stage of the story, when the phenomenon existed, but was not yet fully characterized or named. Rather than focusing on making striking photographic images, she focused on measurement. She used sensitive electrical instruments to compare how strongly different substances ionized air. This approach helped reveal that the emission from uranium was not primarily dependent on its chemical compounds. Whether uranium was in one salt or another, the activity was broadly tied to the uranium content. That observation pointed toward the atom itself as the source, not a rearrangement of atoms in a molecule. This was a conceptual leap, but it was grounded in evidence. Chemistry changes how atoms share electrons and arrange into compounds. If the phenomenon were chemical, changing the compound would likely change the effect dramatically. But if the phenomenon followed the element regardless of chemical form, then the cause had to be deeper. At the time, atoms were not yet understood as nuclei with protons and neutrons and surrounding quantum electron states. The idea that atoms had internal parts was still emerging, and the atom was often treated as a fundamental unit. Radioactivity challenged that view. It suggested that atoms were not always stable, closed units. Some atoms appeared to be active sources of emissions that could change other matter. The discovery phase also included an important moment of anomaly. When Marie Curie tested minerals that contained uranium, she found that certain ores were much more active than would be expected if uranium alone were responsible. The most famous of these was pitchblende, an ore known to contain uranium. The measurement did not match the simple explanation. If the uranium content was what mattered, the activity should have scaled with it. But the ore's activity was stronger. That mismatch was not a small detail. It was a signal that the phenomenon could lead to new elements hidden within mixtures, detectable not by color or taste or ordinary chemical behavior, but by their radioactive signature. This is one reason the discovery of radioactivity rapidly became more than a curiosity. It became a tool for finding matter that did not reveal itself easily otherwise. The emission acted like a beacon. If you purified a sample and the activity increased, you had concentrated the source. If it decreased, you had separated it away. Radioactivity allowed the invisible to guide chemical work. Still, it is important not to let the later story of element discovery dominate this chapter. The core discovery is the recognition that certain materials emit penetrating ionizing radiation spontaneously, without requiring external excitation like sunlight. That recognition shifted the scientific worldview. It suggested that matter could carry internal processes capable of releasing energy on their own, and it implied that the permanence of elements might not be absolute. The word radioactivity came to describe this intrinsic emission, and the field began to grow around it. As scientists continued investigating, they found that radioactive emissions were not all the same. Some emissions were blocked by thin barriers, while others could pass through thicker materials. Some were deflected by electric or magnetic fields, indicating that they carried charge, while others were not deflected, suggesting they were neutral. These differences eventually led to the classification of alpha, beta, and gamma radiation, but even before naming, the experimental behavior revealed that the phenomenon had internal diversity. Radioactivity was not one mysterious ray, it was a family of processes. The discovery also intersected with emerging ideas about electrons. Around the same era, experiments in cathode ray tubes helped establish the electron as a real particle. That mattered because some radioactive emissions behaved like streams of electrons. The broader scientific landscape was changing. The atom was no longer indivisible, and invisible particles were becoming part of accepted reality. Radioactivity fit into this emerging picture as evidence that atoms could transform and emit parts or energy. Another subtle but important point is that radioactivity was discovered and confirmed through careful control of alternative explanations. Scientists had to rule out ordinary light exposure, chemical contamination, and thermal effects. They had to show that the emissions occurred in darkness, that they persisted over time, and that they depended on the presence of certain elements. This is the quiet labor of turning surprise into knowledge. Discoveries become stable, not because they are exciting, but because they survive skepticism. As the phenomenon gained acceptance, it also raised profound questions. Where was the energy coming from? If a material could emit radiation continuously, did it lose mass? Did it cool? Did it run out? At first, these questions did not have satisfying answers, and that uncertainty fueled both fascination and debate. Some researchers proposed that the energy might come from the surrounding environment, or that radioactivity might be a kind of slow chemical reaction. But as evidence accumulated, it became clear that the energy release was tied to transformations within the atom, far beyond ordinary chemistry. This realization would eventually connect radioactivity to nuclear physics and to the deeper structure of matter. In hindsight, the discovery of radioactivity can look inevitable. Yet it depended on a particular convergence. Photographic technology, sensitive enough to register faint effects, experimental culture skilled in controlling variables, electrical instruments capable of measuring tiny currents, and a scientific community ready to accept that invisible entities could be real. Without any one of these, the emission might have been dismissed or misunderstood. With them, it became a doorway into the nucleus. It also matters that the discovery did not emerge from a search for danger or power. It emerged from curiosity about how matter interacts with light and how invisible rays might exist. The first chapter of Radioactivity is not a story of weapons or reactors. It is a story of noticing. It is about learning that the world can act without announcing itself, and that careful experiments can make that silent action visible. If you step back, you can see why this discovery changed the tone of science. It revealed that matter is not always static, and that stability is not guaranteed by simply being an element. Some forms of matter carry within them an internal imbalance, a tendency to change, and yet this change is not chaotic. It follows consistent patterns and can be measured and understood. The universe is not only stranger than we expect, it is also, in a deep way, coherent. There's a quiet existential feeling in that. The same reality that can surprise us also holds itself together through rules that can be learned. The day may have felt noisy and uncertain, but beneath it, the world continues with patient consistency. Even the hidden transformations of matter obey a steady order, and you can let that thought settle like a calm weight, reminding you that you are held inside a universe that changes. Yes, but changes in ways that are understandable, lawful, and strangely dependable. Chapter 4. Measuring the Invisible, Curie's Tools and Methods. Radioactivity, at the moment Marie Curie encountered it, was not yet a polished field with standard instruments and agreed definitions. It was a puzzling behavior of certain materials. They could affect photographic plates and make air conduct electricity, even when kept in darkness and left alone. What turned that puzzling behavior into a science was not only the recognition that something new was happening, but the ability to measure it reliably, compare it across substances, and follow it through complex experiments without losing track of what mattered. Marie Curie's genius in this phase was methodological. She understood that the invisible becomes understandable only when it can be made legible to instruments, and when those instruments can be trusted. The key physical effect she exploited was ionization. When energetic radiation passes through air, It can knock electrons free from atoms and molecules, leaving behind positively charged ions and creating free electrons that can move. Air that is normally an excellent insulator becomes, in a small and measurable way, a conductor. This is an extraordinary bridge between the unseen and the measurable. The radiation cannot be seen directly, but its ability to create charge carriers in air can be detected as an electric current. In modern language, this is a form of radiation detection based on ion pairs, but in Curie's hands it was a new way to translate a mysterious emission into a number. To do this well, she needed sensitive electrical instruments, and she had access to exactly that kind of precision through Pierre Curie's earlier work. Pierre Curie was deeply involved in the study of very small electrical effects. He and his brother had explored the piezoelectric behavior of quartz, the fact that certain crystals develop an electric polarization when mechanically stressed, and conversely can deform slightly when subjected to an electric field. From that line of research came devices capable of producing and measuring tiny charges with unusual stability. Among these was an electrometer arrangement that could detect extremely small currents by measuring how charge accumulated and how it altered an electrical balance. The principle is simple in spirit. If you have a system where a minuscule current slowly charges a capacitor, you can infer the current from the rate at which the potential changes. The practice is demanding because everything that leaks charge or fluctuates in temperature becomes an enemy of accuracy. Marie Curie did not treat these devices as magical boxes. She treated them as instruments that required discipline. Her measurements relied on carefully prepared experimental geometry. A typical arrangement placed a radioactive sample near a region of air enclosed in a metal container, with electrodes that could collect the charges created by ionization. A voltage across the electrodes would encourage ions and electrons to drift toward opposite sides, producing a current that could be measured. The details mattered: the distance between sample and chamber, the surface area of electrodes, the purity and dryness of air, and the stability of the applied voltage could all affect readings. If the goal was comparison between substances, then the geometry had to be kept constant and the environment had to be controlled as well as possible. This is where Curie's approach differs from a more theatrical style of discovery. Photographic plates produce dramatic evidence, but they can be fickle, and their darkness is not easily mapped to absolute intensity. Ionization currents, by contrast, can be placed on a scale. They can be averaged, repeated, corrected, and compared across days. They can reveal small differences that the eye would miss. With this method, Curie could ask questions that were previously out of reach. Does the emission depend on chemical form or only on the presence of a particular element? Is the effect steady over time? Can one mineral be compared quantitatively with another? Does purification concentrate the activity into specific fractions? Reliable measurement also demands a concept of background. Even in a quiet laboratory, small electrical currents can arise from instrument leakage, from natural ionization in the air, and from environmental conditions. Curie had to distinguish the signal produced by her samples from the baseline behavior of her apparatus. That meant taking blank measurements, repeating them, and tracking how they drifted. In modern terms, she was doing background subtraction and instrument calibration, but without the standardized vocabulary that later fields would develop. Her notebooks and published work reveal a patient attention to what we would now call systematic error, the consistent biases and drifts that can mislead an experimenter if they are not recognized. Another essential element of her method was comparison by reference. If you measure a sample today and another sample tomorrow, any change in temperature, humidity, or instrument sensitivity could distort your conclusions. The solution is to anchor measurements to a reference substance whose behavior is stable and known within your system. Curie frequently compared readings to uranium as a baseline, not because uranium was fully understood, but because it provided a consistent point of comparison. This allowed her to express results as relative activities, making her conclusions robust even when absolute calibration was difficult. Relative measurement is often the first step toward absolute measurement, and in emerging sciences, it is frequently the most powerful one. As her work progressed, measurement became not only a way to describe radioactivity, but a way to navigate chemical complexity. When Curie investigated pitchblende and other ores, the problem was that the unknown sources of strong activity were present in extremely small amounts, mixed into large masses of chemically similar material. Ordinary chemical cues, like color changes or precipitates, could not reliably guide the search. Radioactivity did. She and Pierre performed chemical separations and then measured the activity of each fraction. If a fraction became more active, it implied the radioactive substance had been concentrated there. If activity moved elsewhere, the substance had followed. This is measurement as a compass. It turns a blind chemical labyrinth into a guided path. The chemical work itself demanded enormous care. The separations depended on well-established techniques of analytical chemistry, dissolving ore, precipitating groups of compounds, recrystallizing salts, and isolating fractions based on solubility and reactivity. But the novelty lay in how success was judged. In standard chemical discovery, one might look for a new color, a new spectrum, or a new reaction. In Curie's search, the defining trait was intensity of ionization. A fraction could look ordinary and still be extraordinary because it produced a stronger current. In this way, her methods helped establish a new kind of scientific identity, an element characterized by an invisible physical effect rather than by a visible chemical signature. The tools and methods also contributed to a deeper conceptual shift. Because the activity seemed tied to the amount of a particular element present and not strongly to the compound's chemical form, measurement suggested that radioactivity was an atomic property. This conclusion did not come from philosophical belief. It came from the repeated pattern that changing chemistry did not erase the effect. It was as if the atom carried within it a capacity to produce ionizing radiation, regardless of the molecular clothing it wore. That idea pushed science toward the realization that the atom had internal structure and internal processes. In later years, as the field matured, more specialized detectors would appear, but the core logic remains recognizable today. Modern radiation detection often begins with ionization, whether in gas-filled detectors, scintillators that convert energy to light, or semiconductors that create charge carriers in solids. Curie's early instruments were simpler, yet they embodied the same fundamental principle: translate energy deposition into a measurable electrical signal. In that sense, her work sits at the origin of a broad family of techniques that still define how we see radiation. It is also worth noticing how much of her method was a philosophy of patience. When you measure tiny currents, you must wait for stability. When you repeat comparisons, you must accept that nature does not always offer quick clarity. When you pursue a trace component through tons of ore, you must be willing to do the same procedure again and again, checking each step against the instrument. The drama is not in sudden revelation. It is in sustained attention. Scientific truth in this story is built the way a quiet signal emerges from noise, by careful design, repetition, and respect for error. Trusted historical accounts, including Nobel Prize materials and major scientific histories of early radioactivity research, emphasize that Curie's success depended as much on measurement discipline as on theoretical vision. She did not merely discover new substances. She demonstrated how to build a quantitative science around an invisible phenomenon. By the time radioactivity became a major field, it already carried her imprint. The insistence that the unseen must be made measurable, and that measurement must be made trustworthy. There is something gently profound in that. The universe does not announce its deepest workings in a language our senses naturally understand. And yet, with careful tools and honest methods, even the invisible can become part of knowledge. If you let that settle for a moment, it can make your own day feel lighter. Much of life is noise and hurry, but beneath it is a quieter reality that can be approached with patience, and that does not mind if you finally rest. Chapter 5: Polonium and Radium, Finding New Elements Inside Ore. Finding polonium and radium was not a matter of simply noticing something unusual and declaring victory. It was a long, disciplined chase through chemical complexity, guided by the faint but stubborn signal of radioactivity. The challenge was almost paradoxical. The Curies were trying to prove the existence of substances that were present in ore in vanishingly small amounts, substances that did not announce themselves with bright colors, obvious smells, or dramatic reactions. They had to be tracked by an invisible property, measured indirectly, and then separated from a mountain of chemically similar material until the evidence became undeniable. The starting point was pitchblende, a dense uranium-rich ore that had already been processed industrially for uranium compounds. For the Curies, the crucial observation was that some samples of pitchblende were far more active than the uranium content could explain. If uranium were the only source, the activity should have scaled in proportion to uranium concentration. Instead, the ore behaved as if it contained an additional, far more intense source of ionizing radiation. This kind of mismatch is one of science's most valuable signals. It is nature quietly saying, your model is missing something. From there, the problem became chemical. Pitchblende is not one substance. It is a complex mineral mixture containing many elements and compounds intertwined in a stubborn matrix. The only way to isolate an unknown component inside it is to break the ore down chemically and then separate it into fractions based on known chemical behavior. The Curies did not have a direct way to see polonium or radium. They had to use classical chemical techniques: dissolution, precipitation, crystallization, separation by solubility. And after each step, ask the same question: where did the radioactivity go? That question turned measurement into a compass. After each separation, they tested the fractions for their ability to ionize air. The more active fraction was likely to contain more of the unknown radioactive substance. If activity followed a fraction that behaved chemically like a known element, it suggested that the unknown might be chemically similar to that element and traveling with it through the separations. This is the key idea. The new element could be hidden because it mimicked another element in chemical reactions, blending into familiar pathways while remaining physically extraordinary. Polonium came first, and its discovery illustrates this logic. As the Curies processed pitchblende, they found that a highly radioactive component tended to follow the chemistry of bismuth. Bismuth compounds have characteristic precipitation behaviors, and when they isolated fractions enriched in bismuth-like material, those fractions were far more radioactive than bismuth itself should be. The simplest explanation was that the fraction contained an unknown element chemically similar to bismuth but much more radioactive. On that basis, they announced a new element and named it polonium, a deliberate tribute to Marie's homeland, Poland, which at the time was not politically independent. The naming carried scientific meaning, but also a quiet personal statement. Discovery can be a way of leaving a mark on the map of knowledge. When the political map denies your identity, it is important to understand what announcing a new element meant scientifically. It was not merely a claim of novelty. The evidence had to be anchored in reproducible measurements and in a coherent chemical argument. If the unknown activity consistently followed the bismuth fraction through multiple separations, and if no known contamination could explain the intensity, then the hypothesis of a new element became credible. Still, polonium was extraordinarily difficult to isolate as a pure substance, in part because it occurs in such tiny quantities in ore, and because it is radioactive in a way that leads it to diminish with time. In those early years, the proof of polonium was largely inferential and chemical, supported by the consistent, trackable behavior of its activity and by the inability of known elements to account for it. Radium, discovered soon after, demanded an even larger effort and eventually provided a more concrete pathway to isolation. In the Curie separations, another strong radioactive component behaved chemically like barium. Barium is an alkaline earth metal, and its salts have a chemistry that can be manipulated through repeated crystallizations. The unknown radioactive substance stayed with the barium fraction, yet the activity of that fraction was far too strong to be explained by barium itself. Again, the pattern suggested a chemically similar but distinct element hidden within. This set the stage for one of the most physically demanding laboratory campaigns in the history of chemistry. To enrich radium, the Curies needed access to large quantities of pitchblende residues, often the leftover material from uranium extraction. The work involved dissolving, filtering, precipitating, and crystallizing again and again, because radium and barium are chemically so similar that ordinary separation methods only shift the mixture slightly each time. Repetition was not optional, it was the separation strategy. With each cycle, they could create a fraction with slightly higher radium content, then repeat until the radium signature became stronger. What made this process scientifically powerful was that it was not blind repetition. It was guided repetition. The radioactivity measurements acted as feedback, telling them whether a particular crystallization step had enriched the desired fraction or had dispersed it. Over time, this created a convergence toward more concentrated radium salts. The logic is almost meditative. Take a complex mixture, apply a known separation principle, measure the result, keep the part that carries the signal, repeat. Slowly, the invisible becomes concentrated enough to leave unmistakable traces. Eventually, the existence of radium could be supported not only by radioactivity measurements, but also by spectroscopy. Spectroscopy is the study of the light emitted or absorbed by elements, which reveals characteristic lines associated with electron transitions. If a purified fraction shows spectral lines that do not match any known element, it is strong evidence that a new element is present. The Curies and their collaborators used spectroscopy as a crucial supporting method. In addition, they worked to estimate atomic weight, another classical chemical criterion for identifying an element. These steps mattered because science demands multiple independent lines of evidence. Radioactivity alone could reveal that something unusual was present, but spectroscopy and chemical properties helped establish that the unusual thing had a distinct elemental identity. The isolation of radium as a compound, particularly in the form of radium chloride, became one of the iconic achievements of this period. It is easy to underestimate what that meant in practice. The amount of radium in ore is tiny, and isolating even a small quantity required processing immense amounts of material. The labor was chemical, physical, and logistical. It required a kind of stubborn faith in measurement, the belief that if the signal is real and you keep following it honestly, it will eventually lead you somewhere concrete. At the same time, the work carried risks that were not yet understood. The biological effects of intense exposure to radiation were not fully appreciated, and the early culture of radioactivity research often treated these substances with curiosity rather than caution. Luminous materials were handled, stored, and observed in ways that would be unthinkable today. This is not a moral judgment about the past. It is a reminder that scientific discovery often arrives before society fully grasps the consequences of what has been discovered. Polonium and radium also reshaped the meaning of the word element. In the 19th century, elements were largely treated as permanent building blocks. You could combine them, separate them, and rearrange them chemically, but the element itself was thought of as stable. The discovery of intensely radioactive elements suggested that some forms of matter are not merely reactive, they are internally transformative. They emit energy, they produce penetrating radiation, and over time they change into different substances. The periodic table was no longer only a catalog of stable identities. It became a landscape that included instability and time. It is also worth emphasizing that the Curies' achievement was not only intellectual, but institutional. They helped establish radioactivity as a measurable, reproducible domain of physics and chemistry. Their methods created standards for comparison. Their careful documentation allowed other laboratories to confirm findings. Their naming and characterization practices fit within the rigorous culture of chemical discovery. This is how new knowledge becomes part of science, rather than remaining a private marvel. And yet, beneath all that rigor, there is a quiet human story in the process itself. Imagine pursuing something you cannot see, that exists in amounts so small they almost feel philosophical, and trusting that the universe is consistent enough that repetition will eventually reveal it. Polonium and radium were hidden inside ore like whispered facts inside stone. The Curies did not extract them by force of imagination. They extracted them by listening to measurement, step after step, until the stone's whisper became a clear statement. There is a gentle existential reflection here too. You can live an entire life unaware that deep inside ordinary-looking matter, transformations are quietly unfolding on timescales that do not care about your calendar. The world contains realities that are both invisible and utterly lawful. And perhaps that is comforting. Even when your day feels chaotic, the universe is still practicing its quiet order, turning mystery into pattern, and holding you briefly, beautifully, inside the same fabric of rules. Chapter 6. The Three Faces of Radiation: Alpha, Beta, Gamma. When scientists first realized that certain substances emitted rays without being heated, illuminated, or chemically changed in any obvious way, the word ray did more to express mystery than understanding. The emissions were invisible, yet they left traces. Air became faintly conductive, photographic plates darkened, and certain materials glowed. Early on, it was natural to imagine a single kind of outflow, one strange influence streaming from matter. But careful experiments soon made it clear that radioactivity was not one thing. It was a family of phenomena. Different emissions behaved differently when they passed through matter, and they responded differently to electric and magnetic fields. From those differences emerged one of the most clarifying ideas in the early science of radioactivity. There are three distinct faces of radiation, now known as alpha, beta, and gamma. This classification was not invented as a theory first. It was earned through observation. Researchers noticed that some emissions were stopped easily, while others penetrated farther. Some caused dense ionization over short distances, while others were less ionizing but more penetrating. Some were deflected by fields, implying an electric charge, while others were not deflected, implying neutrality. When you cannot see a phenomenon directly, you learn to know it by how it behaves in controlled conditions. Radiation became legible through its interactions. Alpha radiation is the most immediately physical of the three, in the sense that it behaves like a stream of relatively heavy charged particles. The modern understanding is that an alpha particle is a helium nucleus containing 2 protons and 2 neutrons. That makes it much more massive than an electron, and it carries a positive electric charge. This identity was not obvious at first, but it became established through a chain of evidence. Alpha radiation could be deflected by electric and magnetic fields in a way consistent with a positively charged particle. It was strongly ionizing, meaning it produced many ion pairs in air over a short path, and it was relatively easy to stop with thin layers of material. Later, when scientists trapped alpha particles and found that they became helium atoms after capturing electrons, the picture became clear. Alpha emission is literally a nucleus ejecting a small cluster of nucleons that is, in effect, a helium nucleus. Because alpha particles are heavy and charged, they interact intensely with matter. As an alpha particle passes through air or tissue, it experiences strong electromagnetic forces from the electrons and nuclei it encounters. It loses energy quickly, ionizing atoms along its path. This is why alpha radiation has a short range in air and is stopped by very thin barriers. It is also why alpha radiation is so effective at ionization per unit distance traveled. In practical terms, alpha radiation is not very penetrating from outside the body, but it can be hazardous if an alpha-emitting substance is inhaled or ingested and becomes lodged inside tissues, because then the ionization happens directly in living material. Beta radiation, by contrast, behaves like a stream of much lighter charged particles. In modern terms, beta radiation consists of electrons or positrons emitted from the nucleus during certain types of radioactive decay. Beta particles are far less massive than alpha particles and they carry a single unit of negative charge if they are electrons, or a positive charge if they are positrons. Historically, the first recognized beta radiation was deflected in electric and magnetic fields in the opposite direction to alpha radiation, indicating negative charge. Its ability to penetrate matter was greater than alpha's, but it was still attenuated by modest thicknesses of material. Its ionization pattern was typically less dense than alpha's over a comparable distance, in part because its lighter mass and higher speed lead to a more scattered path and different energy deposition behavior. The origin of beta radiation is a beautiful example of how nuclei can adjust their internal balance. In one common type of beta decay, a neutron in the nucleus transforms into a proton, emitting an electron and an antineutrino. In another type, a proton transforms into a neutron, emitting a positron and a neutrino, or the nucleus captures an orbital electron in a process called electron capture. These transformations are governed by the weak interaction, one of the fundamental interactions of nature. The key idea is that the nucleus is not a fixed set of protons and neutrons forever. Under certain conditions, it can change the identity of one nucleon into another, shifting the balance toward a more stable configuration. The emitted beta particle is the visible signature of that internal adjustment. Beta radiation's interaction with matter is strongly shaped by its small mass and charge. Beta particles can be deflected and scattered by electric fields within materials, and they can radiate energy when they are decelerated, producing a kind of secondary radiation known as bremsstrahlung. This is one reason the shielding strategy for beta radiation is more nuanced than simply using the densest material possible. Dense, high atomic number materials can generate more bremsstrahlung when beta particles slow down abruptly, so layered shielding approaches can be used in practice to reduce both the beta particles and any secondary X-rays. The underlying physics is a reminder that stopping radiation is really about managing interactions and energy transfer, not merely placing a wall in the way. Gamma radiation is the third phase, and it is the most wave-like in the classical sense, although in modern physics it is described as high-energy photons, the quanta of the electromagnetic field. Gamma rays carry no electric charge and have no rest mass. They are, in essence, extremely energetic light, though not light that human eyes can see. Unlike alpha and beta radiation, gamma radiation is not a stream of material particles being ejected as such, but a release of electromagnetic energy from the nucleus. It often occurs when a nucleus is left in an excited state after undergoing another decay. The nucleus may rearrange internally, stepping down to a lower energy state by emitting a gamma photon. In that way, gamma emission can be thought of as the nucleus relaxing, shedding excess energy as radiation. Because gamma rays are neutral, they are not deflected by electric or magnetic fields. That neutrality also contributes to their penetrating power. Charged particles lose energy continuously through electromagnetic interactions with electrons in matter, but gamma photons can travel significant distances before interacting at all. Their interactions are more probabilistic. A gamma photon may pass through material without effect, or it may undergo an interaction such as the photoelectric effect, Compton scattering, or at sufficiently high energies, pair production. In the photoelectric effect, the gamma photon transfers its energy to an electron, ejecting it from an atom. In Compton scattering, the gamma photon collides with an electron, transferring some energy and changing direction. In pair production, the gamma photon transforms into an electron-positron pair in the presence of a nucleus, converting electromagnetic energy into matter and antimatter. These are not just technical details. They explain why gamma radiation is hard to stop. It does not gradually slow down in the same continuous way as a charged particle. Instead, it either interacts in a discrete event or it does not, and you must use sufficient thickness and appropriate materials to make interactions likely. The historical separation of alpha, beta, and gamma was strengthened by simple but powerful experiments. Researchers placed absorbers of different thicknesses between a radioactive source and a detector. They observed how quickly the signal dropped. One component vanished almost immediately, another diminished more gradually, and another persisted more stubbornly through greater thickness. They also applied magnetic and electric fields and watched how the radiation's path bent. The strongly ionizing component bent one way, the other charged component bent the opposite way, and a third component did not bend. Out of that experimental clarity came the threefold classification that still anchors how we talk about nuclear radiation today. These three kinds of radiation also differ in how they deposit energy, and that difference matters for biological effects. Alpha particles deposit energy densely along short paths, creating concentrated ionization. Beta particles deposit energy less densely and can travel farther, producing more diffuse ionization. Gamma rays deposit energy in a still more spread out way, often through secondary electrons produced when gamma photons interact. The biological consequence is not only about how much energy is delivered, but about how it is distributed in microscopic space. Dense ionization can produce more severe localized damage, while more diffuse ionization spreads effects out. Modern radiation protection and medical uses of radiation rely on these distinctions, using controlled doses and shielding strategies built around the known interaction mechanisms. At the same time, these distinctions taught scientists something profound about the nucleus. Alpha emission implies the nucleus can eject a tightly bound cluster. Beta emission implies the nucleus can change a neutron into a proton, or vice versa, reshaping the element's identity. Gamma emission implies the nucleus has quantized energy states and can release energy as a photon without changing its proton count. In other words, the three faces of radiation are also three windows into nuclear structure. They reveal that nuclei are not featureless lumps. They have internal organization, stability patterns, and allowed transitions. The atom's core is not merely heavy. It is dynamic. It is easy, in modern hindsight, to forget how revolutionary this was. Before radioactivity was understood, matter's deepest changes were mostly thought to be chemical, happening in the electron cloud. The classification into alpha, beta, and gamma showed that the nucleus is a stage for processes entirely beyond chemistry. It also created a language that allowed the field to grow rapidly, because scientists could now talk precisely about what they were observing. They were no longer chasing a single mysterious ray. They were studying distinct emissions with distinct behaviors, each one measurable and testable. There is also a quiet elegance in how the universe offers clues. Alpha, beta, and gamma are not labels imposed on nature. They are names for differences that nature itself makes obvious when we look carefully. The invisible becomes organized when we ask the right questions. We learn to distinguish what once felt like one mystery into three patterns, and those patterns become stepping stones to deeper understanding. And if you let your mind rest on that idea, there's something gently existential in it. Your life is lived at a scale where the atom seems solid and stable. Yet within matter, there are emissions that can cross space without sound, carrying signatures of transformation. The universe is not only vast, it is layered, with quiet processes beneath the surface of the everyday. You do not have to solve any of it tonight. You can simply feel the calm of knowing that reality has structure and that even its hidden energies follow rules, steady enough to be learned and patient enough to wait while you let the day go. Chapter 7: Half-Life and the Clock Inside Matter. Among all the ideas that radioactivity introduced into science, half-life is one of the most quietly astonishing. It takes a phenomenon that feels unpredictable and turns it into something that behaves like a clock. It explains how a material can change spontaneously without any external trigger, and yet do so in a way that can be measured with calm reliability. Half-life is not merely a convenient number written next to an isotope in a table. It is a statement about how probability becomes order when you look at many atoms together. To understand half-life, it helps to start with what radioactive decay is at the most basic level. Some atomic nuclei are unstable, meaning they have an internal configuration that can transform into another configuration that is more stable. The transformation is not driven by temperature or pressure in ordinary circumstances, and it is not a chemical reaction. It is a nuclear event, governed by the rules that apply inside the nucleus. When such a nucleus decays, it changes into a different nucleus, often emitting radiation as part of the process. The key point for half-life is that for an individual nucleus, the timing of that change is fundamentally unpredictable. You cannot watch one specific unstable atom and say exactly when it will decay. This unpredictability is not due to ignorance in the ordinary sense, as if we simply do not have a good enough microscope. It is a feature of quantum processes. In many radioactive decays, the nucleus must pass through a barrier in a way that resembles quantum tunneling, or it must undergo a transformation governed by the weak interaction. In either case, the decay is described by a probability per unit time. The nucleus has a certain chance of decaying in the next moment, and if it does not decay, it has a similar chance in the next moment. The nucleus does not age in the way living things do, becoming more likely to decay simply because time has passed. Instead, the process is memoryless in a precise statistical sense. An unstable nucleus that has survived for a long time is not closer to decay than one that was created recently. At any given moment, it has the same probability of decaying as it did before. This memoryless behavior is the foundation of the half-life concept. When you have a very large number of identical unstable nuclei, each one has the same probability of decaying per unit time. Because of that, the collection as a whole decays in a smooth, predictable way, even though each individual event is random. Over time, a constant fraction of the remaining nuclei will decay in each equal interval of time. This is why the decay curve is exponential, though you do not need the mathematics to feel the intuition. The more atoms remain, the more decays occur per unit time. As fewer remain, fewer decays occur, and the process slows. It is like a crowd leaving a stadium through many exits. At first the flow is heavy, then gradually less, not because the exits change, but because the crowd becomes smaller. Half-life is defined as the amount of time it takes for half of the radioactive nuclei in a sample to decay. if you start with a certain amount of an isotope, then after one half-life, you have half of the original nuclei remaining, on average. After another half-life, half of what remains decays again, leaving a quarter of the original. This pattern continues, creating a steady, predictable progression of shrinking fractions. What makes this powerful is that it does not depend on the sample being large in the everyday sense. It depends on the number of atoms being large, which is almost always true in macroscopic samples. Even a tiny speck contains an enormous number of atoms, enough that the statistics become smooth and the half-life becomes meaningful. Half-life is often misunderstood as a kind of countdown timer in each atom, as if every nucleus is scheduled to decay at a precise moment. That is not how it works. Half-life is a property of a population, not an appointment book for individuals. A particular nucleus might decay soon, or it might persist far longer than the half-life. Half-life is about averages and probabilities. It tells you what will happen in the collective behavior of many atoms, not the fate of any single one. That is why a sample can follow a very stable decay law, even though the underlying events are random. It is one of the most beautiful examples of how randomness at a small scale can produce order at a large scale. Different isotopes have vastly different half-lives. Some decay extremely quickly, while others decay so slowly that they remain detectable across geological timescales. The reason half-lives vary so widely lies in nuclear structure and decay mechanisms. In alpha decay, for example, the nucleus must emit an alpha particle, and the probability of that emission depends strongly on the height and width of the effective barrier the alpha particle must overcome. Quantum tunneling makes it possible, but the likelihood can be very small, leading to long half-lives, or relatively larger, leading to shorter ones. In beta decay, the transformation of a neutron into a proton or vice versa depends on the energetics of the nuclear states involved and the rules of the weak interaction, which can also lead to a wide range of decay rates. In gamma emission, which often follows another decay, the half-life can be extremely short because the nucleus is simply shedding excess energy. The point is that half-life is not arbitrary. It encodes deep information about the structure and stability of nuclei. Half-life also connects to a measurable quantity called activity, which is the rate at which decays occur in a sample. A sample with a short half-life tends to have a high activity for a given number of atoms because a larger fraction decays per unit time. A sample with a long half-life has a lower activity for the same number of atoms because decays are rare. This is another important intuition. A long half-life does not mean weak in the sense of harmlessness. It means the decay rate is slow, which can still be significant depending on how many atoms are present and what kind of radiation is emitted. But in many contexts, activity is a practical way to connect the abstract idea of half-life to what instruments detect. The clock-like nature of half-life is what allows radiometric dating. If you know the half-life of an isotope, and you can measure the ratio between the isotope and its decay product, you can infer how long the system has been evolving since a certain starting condition. For example, if a mineral crystal forms and incorporates an unstable isotope but excludes its decay product, then over time the decay product accumulates inside the crystal. Measuring the ratio can reveal the time since the crystal formed. This method is powerful because it does not rely on human records or environmental memory. It relies on nuclear processes that are largely insensitive to ordinary chemical and physical conditions. That makes it a kind of deep clock, operating within matter itself. However, the word clock can be misleading if it suggests perfect simplicity. In practice, radiometric dating requires careful assumptions about whether the system remained closed, whether the initial amounts are known or can be inferred, and whether contamination occurred. These are matters of geology and chemistry layered on top of nuclear physics. But the nuclear physics foundation is remarkably stable. The half-life is a property of the nucleus. In ordinary conditions, it does not change meaningfully with temperature, pressure, or chemical environment. There are rare special cases involving electron capture where extreme conditions can slightly affect decay rates by altering electron availability, but for most isotopes in most contexts, half-lives are effectively constant across the environments of Earth and beyond. This constancy is what makes half-life such a trustworthy concept in science. Half-life also matters in medicine, where radioactive isotopes can be used as tracers or for therapy. And the half-life determines how long the isotope remains active in the body or in a medical setting. It matters in astrophysics as well, where radioactive isotopes can serve as markers of processes in stars and supernova remnants. It matters in environmental science, where isotopes can be used to track water movement or pollutant ages. In each case, half-life is the same underlying idea, a predictable statistical decay law arising from quantum processes inside nuclei. There is another subtle and calming lesson in half-life. The idea that predictability does not always come from control. In daily life, we often imagine that if something is predictable, it must be tightly controlled, like a machine following commands. Half-life shows a different kind of predictability, a predictability that emerges from freedom and randomness. Each atom is free to decay at any moment without being scheduled, without being pushed, and yet the collective behavior forms a stable curve. This is the universe offering order without needing a supervisor. It is a kind of natural self-averaging. This self-averaging also helps explain why early scientists could make reliable measurements of radioactivity long before they fully understood nuclear structure. They could measure the rate of ionization in air, the fading of activity over time, and the relationship between activity and quantity of material. Those measurements were consistent because the statistical laws were consistent. Even when the deepest mechanism remained mysterious, the decay patterns were steady enough to build a science upon. Half-life is, in a sense, a bridge between two views of time. On one side is the human view, where time feels personal and uneven. Some days rush, some drag, and memory distorts the calendar. On the other side is nuclear time, where change is governed by a fixed probability per unit time, indifferent to mood, season, or story. The atom does not know whether it is day or night. It simply exists in a state that has a certain chance to transform, and it repeats that chance moment by moment. When you realize that, it can evoke a quiet existential thought. There are clocks inside matter that have been ticking since long before you were born, and will continue long after today's concerns have faded. And yet, you are here, a brief arrangement of atoms capable of noticing those clocks and turning them into understanding. In the vast, indifferent steadiness of nuclear time, your awareness is a rare kind of light. And perhaps that is enough reason to let the day soften and let yourself rest. Chapter 8. Energy from the Nucleus. Why Decay Releases Power. Radioactive decay is often introduced as a story about particles and rays, about alpha, beta, and gamma emissions that can be detected and classified. But beneath that outward behavior is a deeper and more surprising fact. Decay releases energy, and the amount of energy involved is far larger than anything typical chemical changes can produce per atom. This is the quiet reason radioactivity reshaped physics. It forced scientists to confront a new category of energy storage inside matter, hidden in the nucleus itself, and it revealed that the atom's core is not merely massive and compact, but also a reservoir of binding energy held in place by fundamental forces. To understand why decay releases energy, the first idea to hold gently is that nuclei have different degrees of stability, and stability is tied to energy. In physics, systems tend to move toward states with lower energy, not as a moral rule, but as a consequence of how forces and constraints work. A ball rolls downhill because gravity makes lower gravitational potential energy more stable. A stretched spring relaxes because the relaxed state is lower energy given the spring's internal forces. In the same calm way, an unstable nucleus transforms because there exists a configuration of nucleons with lower total energy, and the transformation allows the nucleus to approach that lower energy state. The nucleus is built from protons and neutrons, which are bound together by the strong interaction. This force is extraordinarily powerful at very short ranges, strong enough to overcome the electromagnetic repulsion between positively charged protons when they are close together. But the balance inside the nucleus is delicate. Protons repel each other. Neutrons help stabilize many nuclei by contributing strong force attraction without adding electric repulsion, and the whole system obeys quantum rules that limit how nucleons can arrange themselves. A nucleus is not a simple pile of particles. It is a quantum system with allowed configurations and forbidden ones. Some combinations of protons and neutrons settle into stable structures. Others sit in arrangements that can lower their energy by changing composition or ejecting part of the nucleus. That brings us to binding energy, a concept that explains why energy can be released when a nucleus changes. Binding energy is the energy required to separate a nucleus completely into individual protons and neutrons. If you imagine pulling a nucleus apart, you would need to do work against the strong interaction, and that work is stored as energy in the separated pieces. Conversely, when nucleons bind together to form a nucleus, energy is released because the bound state is lower energy than the unbound state. The nucleus is like a deep energy well created by the strong interaction. The deeper the well, the more stable the nucleus, and the more energy was released when it formed. A remarkable fact, confirmed by careful measurements, is that the mass of a bound nucleus is slightly less than the sum of the masses of its separated protons and neutrons. This difference is called the mass defect, and it is not a bookkeeping error. It is a physical signature of binding energy. Energy contributes to mass in relativity, so when energy is released as nucleons bind, the resulting bound nucleus has less mass than the free nucleons by an amount corresponding to the released energy. This is one of the most concrete ways the equivalence between mass and energy shows up in ordinary laboratory measurements. You do not need equations to grasp the idea. If energy leaves the system's mass is slightly reduced, because mass is a form of energy. Now consider a radioactive decay. In many decays, the nucleus changes into a different nucleus that has a higher binding energy per nucleon, meaning it is more tightly bound and therefore lower in total energy. When the nucleus moves to that more stable configuration, the difference in energy must go somewhere. It appears as kinetic energy of emitted particles, as energy carried by photons, or as energy carried away by neutrinos in beta processes. The energy is not created from nothing. It is released from the difference in nuclear binding energy between the initial and final states. The nucleus is, in effect, stepping down into a deeper well, and the drop in energy becomes radiation. Alpha decay is a clear example of this logic. When a heavy nucleus emits an alpha particle, it reduces its proton and neutron count in a particular way. The daughter nucleus plus the alpha particle together can have a lower total energy than the original nucleus. The difference appears mainly as kinetic energy of the alpha particle and the recoiling daughter nucleus. The reason alpha decay happens at all is connected to the stability landscape of heavy nuclei and the fact that the alpha particle is itself a very tightly bound cluster. Emitting a tightly bound cluster can be energetically favorable, and quantum tunneling allows it to occur even though the alpha particle must effectively escape through a barrier formed by nuclear attraction and electromagnetic repulsion. Beta decay reveals a different kind of energy reasoning. In a common form of beta decay, a neutron transforms into a proton, emitting an electron and an antineutrino. This transformation occurs when the nucleus can lower its energy by changing its proton to neutron balance. But energy and momentum conservation must still hold. The emitted electron and antineutrino share the available energy in a continuous range, which was historically puzzling until the neutrino concept was introduced. The existence of the neutrino was not a decorative addition. It was required to preserve the conservation of energy and momentum in beta decay. In this way, radioactive decay also drove the development of particle physics. It forced scientists to accept that unseen particles could carry away energy and angular momentum, leaving only a subtle signature. Gamma emission is often the simplest to picture energetically. After a decay, the daughter nucleus may be left in an excited state, meaning its internal arrangement has extra energy. It can release that energy by emitting a gamma photon as it transitions to a lower energy configuration. This is similar in spirit to how atoms emit visible light when electrons drop between allowed energy levels, except that gamma emission involves energy changes in the nucleus rather than in the electron cloud, and therefore the photon energies are typically much higher. Gamma emission is nuclear relaxation, the nucleus shedding energy to become more stable without changing its number of protons or neutrons. This nuclear energy scale is why radioactive processes feel so powerful compared to chemistry. Chemical reactions involve rearrangements of electrons and changes in electromagnetic potential energy between atoms. Those energies are significant in everyday life, powering metabolism, fires, batteries, and industrial chemistry. But nuclear binding energies arise from the strong interaction, which is vastly more intense at the scale of the nucleus. Per unit mass of material, nuclear processes can release energy orders of magnitude greater than chemical processes. This does not mean radioactive decay is always dramatic. Many decays are slow and gentle in their total power output because they occur infrequently. But each individual decay event carries a substantial energy packet compared to chemical events at the atomic level. The release of energy in decay is also so intimately connected to the idea of stability valleys and peaks in nuclear physics. If you plot nuclei by proton and neutron number, stable nuclei occupy a region often called the Valley of Stability. Unstable nuclei tend to move toward this region through decays that change their composition. Heavy nuclei may decay by alpha emission, stepping down in size. Nuclei with too many neutrons may undergo beta decay to convert neutrons to protons. Nuclei with too many protons may undergo beta plus decay or electron capture to convert protons to neutrons. Each of these pathways is an energy-lowering route. The decay is nature performing a quiet optimization, not with intention, but with physical necessity. It is worth lingering on how carefully this has been verified. The energies of emitted alpha particles can be measured. The spectra of gamma rays can be recorded with high precision, and the energy distributions in beta decay can be mapped. The match between measured energy release and predicted differences in nuclear mass and binding energy is one of the strongest confirmations of modern nuclear physics. It also provides a deep consistency check across fields. Precision mass measurements, radiation spectroscopy, and particle detection all converge on the same energy accounting. The nucleus does not violate conservation laws. It follows them with relentless exactness. At the same time, there are subtleties that make this subject richer than a simple energy comes out story. In beta decay, for example, not all energy is deposited locally because neutrinos interact extremely weakly with matter and can escape, carrying energy away without leaving much trace. In gamma interactions, energy deposition depends on whether photons are absorbed or scattered, and on the secondary electrons they produce. In alpha decay, energy deposition is very local because alpha particles interact strongly with matter and stop quickly. These differences matter for radiation detection, for biological effects, and for how decay energy translates into heat in a material. Energy release is universal in decay, but how that energy appears in the world depends on the radiation type and the environment. Another subtle and profound point is that decay does not drain the nucleus the way a battery drains in a continuous flow. Each decay event is discrete. A nucleus remains in its initial state until it suddenly transforms, and then it is no longer that nucleus at all. The energy release is associated with that change of identity. The nucleus is not leaking energy steadily like a warm object. It is undergoing rare quantized transitions. This is one reason radioactive materials can remain stable-looking for long periods while still being sources of radiation. The decays are scattered in time among an enormous number of atoms, producing an overall steady activity, but each atom's transformation is a single event. If you connect this back to Marie Curie's era, you can see why the question of energy was so haunting. Early researchers could detect radiation and measure its ionizing power, but the source of the energy was mysterious. Chemical explanations could not account for it. Only when the nucleus and binding energy concepts matured did the puzzle gain a clear answer. The energy comes from differences in nuclear binding, and its magnitude reflects the strength of the forces inside the nucleus. This revelation did not make the world less strange. It made it more coherent. The mystery became a map. There is an existential reflection tucked into that coherence. Inside the atoms that form your body and everything around you, energy is stored not only in chemical bonds, but in the deep architecture of nuclei, shaped by forces that have been operating since the earliest moments of the universe. Some of that energy is released in slow, patient transformations that pay no attention to human schedules. And yet you can understand it. You can hold the idea in your mind. For a brief time, matter has arranged itself into a listener who can notice the universe noticing itself. Chapter 9. Radioactivity in the world around you. Radioactivity can feel like a property of laboratories, something that belongs to lead-lined rooms, warning symbols, and specialized instruments. That impression is understandable because the most dramatic uses of radioactive materials in history have been tied to medicine, industry, and energy research. But the deeper truth, supported by decades of careful measurement in physics, geology, and environmental science, is that radioactivity is also part of the background fabric of ordinary life. It is in the ground beneath your feet, in the air you breathe, in some of the food you eat, and in the constant drizzle of particles arriving from space. Most of the time, it is present at low levels, and your body and the world handle it without any sensation at all. The planet has never been radiologically silent. Life evolved in a world where radiation existed. A good place to begin is with the idea of background radiation. Background radiation is the ionizing radiation that is always present, independent of any specific human activity. It comes from several sources, and the mix depends on where you live, how high above sea level you are, what kinds of rocks are under and around your home, and even what building materials were used in the structures around you. The word background does not mean trivial. It means baseline. It is what remains even when we remove all deliberate radioactive sources and simply listen to the planet. One major contributor is natural radioactivity in Earth's crust. The Earth formed from material that contained a variety of elements, including long-lived radioactive isotopes that have not yet fully decayed away. Among the most important are isotopes in the uranium and thorium decay chains, and a naturally occurring radioactive isotope of potassium. Uranium and thorium are present in many rocks in low concentrations, and as they decay, they produce a series of daughter isotopes, some of which are also radioactive. This creates a cascade of transformations, with different radiation emissions along the way. Potassium's radioactive isotope is present because potassium is a common element in rocks and in living tissues, and a small fraction of naturally occurring potassium is radioactive. The result is that the ground itself is a slow, steady source of radiation, and it has been so throughout the history of life. This does not mean the ground is dangerous in an everyday sense. It means the planet is active. The intensity varies. Regions with granite-rich geology often have higher natural background levels than regions dominated by other rock types, because granite can contain higher concentrations of uranium and thorium. Beaches can have naturally elevated radioactivity if their sands contain heavy minerals rich in thorium. Places where certain ores occur naturally can also have higher levels. But even when variations exist, the concept remains the same. Nature provides the baseline. Another important contributor is radon gas, which is especially interesting because it connects the solidity of rocks to the air inside homes. Radon is a noble gas produced in the decay chain of uranium. Because it is a gas, it can migrate through pores and cracks in soil and rock and enter the atmosphere, including the indoor air of buildings. Outdoors, radon is usually diluted quickly. Indoors, especially in basements and lower floors of buildings with poor ventilation, radon can accumulate. Radon itself decays, and its decay products can attach to airborne particles and be inhaled, exposing lung tissue to radiation. This is why radon is often discussed in public health. It is a natural source of exposure that can, in some circumstances, be significant, and it can be mitigated by ventilation and building measures. The remarkable point is that a major part of human radiation exposure globally can come not from machines, but from the quiet chemistry of the earth beneath our homes. Cosmic radiation is another constant presence. Space is not empty of energetic particles. The sun emits charged particles in the solar wind and, during solar storms, can increase particle flux in ways that affect technology and radiation levels at altitude. Beyond the solar system, the galaxy contributes cosmic rays, which are high-energy particles, mostly protons and atomic nuclei, accelerated by astrophysical events such as supernova remnants and other energetic processes. When these particles strike Earth's atmosphere, they produce showers of secondary particles, including muons and other components, some of which reach the ground. The atmosphere and Earth's magnetic field protect us by absorbing and deflecting much of this radiation, but not all. This is why radiation levels tend to increase with altitude. Air travel exposes passengers and crew to higher cosmic radiation than at sea level, and people who live at high elevations typically have higher background exposure than those near sea level, all else equal. Again, this does not need to be alarming. It is simply a reminder that the sky is not only a source of light and weather, but also a source of energetic particles. Radioactivity is also present inside your body. This can sound unsettling until you recognize it as a natural consequence of living on a planet where certain elements are common. Potassium is essential for nerve function and cellular processes, and because a small fraction of natural potassium is radioactive, your body contains a small amount of radioactivity simply by being alive. Carbon also has a radioactive isotope created in the upper atmosphere by cosmic rays, and this carbon becomes part of the carbon cycle, entering plants through carbon dioxide, moving through food webs, and becoming part of living tissue. The amount is low, but it is measurable. The fact that your body contains trace radioactivity is not a sign of contamination. It is a sign that biology is built from the same elements that circulate through Earth's natural systems. There are also everyday materials that have trace radioactivity due to their mineral content. Some building materials made from stone or mineral aggregates contain small amounts of uranium, thorium, or potassium. This can slightly elevate indoor background levels, though typically within the range of natural variation. Certain ceramics, glass, and other materials can contain trace radioactive elements. Historically, some consumer products contained more noticeable radioactive components, but modern regulations and awareness have greatly reduced such uses. The broader point remains: radioactivity is not confined to rare substances. It appears wherever certain elements appear, and those elements are part of Earth. Understanding radioactivity in the world around you also requires understanding dose in a conceptual, non-alarming way. Radiation is not good or bad in the abstract. It is energy transferred to matter in a way that can ionize atoms and molecules. Biological effects depend on how much energy is deposited in tissues, over what time period, and by what type of radiation. Your body has repair mechanisms that constantly respond to many kinds of molecular damage, not only from radiation, but from normal metabolic chemistry. At low background levels, the body's repair processes handle the resulting damage without noticeable effect. At higher doses, especially delivered rapidly, damage can outpace repair and increase risk. This is the reason radiation protection focuses on minimizing unnecessary exposure while recognizing that background exposure is part of life. In science and medicine, the goal is not to eliminate radiation from the world, which is impossible, but to understand it well enough to manage it intelligently. This perspective is supported by large bodies of research in health physics and epidemiology, including studies of occupational exposure, medical imaging, environmental sources, and populations living in regions with higher natural background. The scientific consensus is not that all radiation is harmless, nor that all radiation is catastrophic. The consensus is that risk depends on dose, dose rate, and radiation quality, and that responsible use and monitoring matter. In everyday life, the most practical point is that natural background radiation varies and is usually low, and that the most significant naturally occurring exposure concern in many settings is indoor radon, which can be measured and mitigated. This is science turning an invisible presence into something that can be understood and managed without fear. Radioactivity also leaves its fingerprints in the planet's history. Heat inside Earth, which drives geothermal gradients, mantle convection, and plate tectonics, is partly sustained by the decay of radioactive isotopes. The planet's interior is warm, not only because it retained heat from formation, but because it continues to generate heat internally through radioactive decay. In that sense, radioactivity is not merely a background hazard or a laboratory phenomenon. It is part of what keeps Earth geologically alive. The slow decay of uranium, thorium, and potassium contributes to the engine that shapes continents, builds mountains, and powers volcanic activity over vast timescales. The world you live on is not static, partly because nuclei quietly change in the dark. Even the tools we use to understand time rely on natural radioactivity. Carbon dating depends on the presence of radioactive carbon in living systems and its decay after death. Geological dating methods depend on long-lived isotopes in minerals. In other words, radioactivity is not only in the world, it is one of the reasons we can measure the age of the world. It is a natural archive mechanism. Matter contains clocks, and the environment supplies their starting conditions through cosmic ray interactions and geological formation processes. When you take all of this together, radioactivity becomes less like an exotic threat and more like an ordinary feature of reality. It is a reminder that the universe is active at all scales. Even stones and air are not inert. They participate in slow transformations that release energy and produce measurable effects. Yet this activity is not loud. It is usually quiet enough that life can flourish on top of it, and that thought can widen into something existential. You are living inside a planet that is gently radioactive, beneath a sky that sends particles from distant cosmic events, inside a body that carries trace isotopes as part of being alive. None of it needs to feel frightening. It can feel grounding, a reminder that you are woven into the same physical story as the Earth and the stars. The day's worries are real, but they are small on the scale of the processes that have been unfolding around you, patiently for eons. You can let that scale soften you and allow yourself to rest inside it. Chapter 10. The Legacy from Curie's Era to Medicine, Radiometric Dating, and the Cosmos. When Marie Curie's work brought radioactivity into the center of scientific attention, it did more than reveal new elements and a new kind of atomic behavior. It changed what it meant to study matter. It gave science a doorway into the nucleus, and it produced tools and concepts that would ripple outward for more than a century, shaping medicine, geology, archaeology, and even our understanding of the universe. The legacy is not a single invention or a single application. It is a widening circle, a set of methods for detecting invisible processes, a new understanding of energy and transformation, and a practical ability to use nuclear change as both a probe and a tool. One part of that legacy is medical. The idea that invisible radiation can pass through matter and interact in measurable ways immediately suggested diagnostic possibilities. X-rays, discovered around the same era, became one of the earliest medical imaging technologies because they could reveal bones and dense tissues without surgery. Radioactivity added new capabilities. Certain radioactive isotopes can be introduced into the body in carefully controlled quantities, and because they emit radiation that can be detected outside the body, they can act as tracers. A tracer is not used primarily to harm tissue, but to follow a biological process. If an isotope behaves chemically like an element used by the body, it can participate in metabolism, blood flow, or organ uptake. Detectors outside the body can then map where the tracer accumulates, turning the body's invisible chemistry into an image. This is the foundation of nuclear medicine. It includes imaging techniques that detect gamma photons emitted by tracers, allowing clinicians to see functional activity rather than only anatomy. In contrast to purely structural imaging, which shows shapes and densities, tracer imaging can show how tissues are working. It can reveal, for example, how blood perfuses an organ, how bones remodel, or how certain glands concentrate specific compounds. The scientific importance of this is profound. Radioactivity became a way to watch physiology in action without opening the body, by translating biochemical pathways into detectable signals. Radiation also became a tool for treatment. The idea that radiation can damage rapidly dividing cells led to radiotherapy, where carefully planned radiation doses are delivered to target tumors while minimizing exposure to surrounding healthy tissue. The physics here is not mystical. Ionizing radiation deposits energy in tissue, producing ionization and molecular changes that can damage DNA. Cells have repair mechanisms, but if damage is extensive or repeated, cells can fail to replicate successfully. Cancer cells, which often divide more rapidly and may have impaired repair pathways, can be more vulnerable. The practice of radiotherapy is built on detailed understanding of dose, radiation type, tissue sensitivity, and geometry. Modern radiotherapy is a field of precision engineering as much as biology, using imaging, planning algorithms, and controlled beams to shape where energy is deposited. It is important to note that the medical legacy is inseparable from the growth of radiation safety. Early researchers did not fully appreciate biological risks, and historical accounts document injuries and illnesses that arose before protective practices were established. Over time, radiobiology and epidemiology built a clearer picture of dose-related risks, and health physics emerged as a discipline focused on monitoring, shielding, and minimizing unnecessary exposure. The modern medical use of radiation is therefore not simply radiation as a tool, but radiation as a tool governed by careful protocols, justified by clinical benefit, and continuously refined to reduce harm. Another major legacy is radiometric dating, which transforms half-life from an abstract property into a practical method for measuring time itself. The core idea is that certain isotopes decay into daughter products at predictable rates. If you can determine how much parent isotope remains and how much daughter product has accumulated, you can infer how long the system has been evolving since a particular starting condition. The simplest conceptual case is one in which a material begins with parent isotopes and no daughter product, and then the daughter accumulates over time. Real systems can be more complex, but the principle remains. Nuclear decay provides a clock that is largely independent of ordinary environmental conditions. This has had enormous impact on geology and earth science. By dating minerals and rocks, scientists can reconstruct the age of Earth's crust, the timing of volcanic events, the formation history of mountain belts, and the tempo of planetary processes. Radiometric dating underpins the modern geological timescale and provides quantitative anchors for evolutionary history and climate history. It is not a single technique, but a family of techniques, each suited to different time ranges and materials. Long-lived isotopes allow dating over very long spans, while shorter-lived isotopes can date more recent events. The reliability comes from the stability of nuclear decay rates and from the ability to cross-check dates using different isotopic systems and different minerals. This cross-validation is a hallmark of mature science. Independent methods converging on consistent timelines. Radiometric dating also shaped archaeology and the study of human history. The presence of radioactive carbon in the biosphere and its decay after death allows dating of organic materials over historical and prehistorical timescales. This method does not read memory from texts, it reads time from matter. It can date wood, charcoal, textiles, bone collagen under appropriate conditions, and other organic remnants, providing a way to place human artifacts and events on an absolute timeline. Calibration with tree rings and other records improves accuracy and accounts for variations in atmospheric carbon production over time, demonstrating again how nuclear physics and Earth system science must work together for precise results. The legacy extends beyond Earth into the cosmos. Radioactivity is part of how the universe makes and transforms elements. The elements heavier than hydrogen and helium are forged in stellar interiors and in violent cosmic events. In stars, nuclear fusion builds heavier nuclei up to certain limits, releasing energy that powers starlight. In explosive environments such as supernovae and neutron star mergers, rapid capture processes can build very heavy nuclei, many of which are unstable and decay towards stability over time. These decays release radiation and heat that influence the evolution of the ejected material. In a real sense, radioactivity is part of the afterglow of cosmic creation, a way that newly formed matter settles into stable forms. Observational astronomy has used radioactive isotopes as probes of these processes. Certain gamma-ray lines observed from space are signatures of specific radioactive decays, allowing scientists to trace nucleosynthesis in the galaxy. The presence of radioactive isotopes in meteorites and early solar system materials provides evidence about the environment in which the solar system formed. Short-lived radionuclides incorporated into early planetesimals could provide internal heating, influencing differentiation, melting, and geological evolution of small bodies. This means radioactivity is not only a tool for dating, it is also a physical engine that shapes planets and asteroids from within. Radioactivity also contributes to the thermal histories of planets, including Earth. Long-lived radioactive isotopes provide a continuing source of internal heat, supporting mantle convection and plate tectonics over geological time. This connection between the nucleus and the surface world is easy to overlook. The slow transformations of atoms deep underground help power the movement of continents and the recycling of crust. The planet's habitability is linked, in part, to a steady internal heat budget, and radioactivity is one component of that budget. The nucleus, though tiny, participates in shaping landscapes. Beyond applications, the legacy includes a shift in how science thinks about matter and energy. Radioactivity provided a direct demonstration that atoms can change identity, that energy can emerge from the nucleus, and that conservation laws still hold in these transformations when all participants are accounted for. The development of nuclear physics and particle physics followed, bringing deeper understanding of the forces inside the nucleus and the particles involved in decay. Concepts such as the neutrino were introduced to preserve conservation in beta decay, and later confirmed experimentally, illustrating how radioactivity pushed science to accept entities that are nearly undetectable but essential to coherent theory. This is part of the broader legacy. Radioactivity trained physics to respect the unseen when evidence demands it. It also trained society to live with a dual reality. Radiation can heal and it can harm, it can reveal and it can destroy, and responsible use requires measurement, transparency, and discipline. The emergence of standards, units, safety procedures, and regulatory frameworks was not merely bureaucratic. It was the social extension of the same methodological lesson Curie embodied. The invisible must be made measurable, and measurement must be made trustworthy. In the end, Marie Curie's era looks both distant and strangely close. The instruments have changed, the theories have deepened, and the applications have expanded into domains she could not have fully imagined. Yet the core remains the same. Matter contains processes that are quiet, lawful, and profoundly informative if you learn how to listen to them. Radioactivity became a language the universe speaks through rocks, bodies, and starlight, and there is a gentle existential reflection in that language. The atoms around you hold memories of ancient events, stellar explosions, planetary formation, geological ages, and biological cycles. For a brief time, you are the part of the universe that can read those memories, not with intuition alone, but with science as a calm method of attention. The day can feel heavy, but the cosmos is still there, vast and orderly, and you can let that vastness hold you softly as you rest. And that's the quiet legacy of Marie Curie's radioactivity, an invisible process that helped us understand medicine, time, and even the cosmos. If you're still awake, my friend, you can tap another video on the channel and keep drifting with me a little longer. And if you're already slipping under, that's perfect too. Sweet dreams among the stars.